Hi there. I have prepared a presentation on large pre-training data sets that power large language models. Essentially, one may find in popular media these days various facets of or various themes around this technology of LLMs that offer some clarity into what makes LLMs tick. And so in this talk, I've chosen to focus on just the pre-training data sets. And I would like to take the viewer through a journey of various pre-training data sets that have been introduced from the most earliest LLMs that were released, such as BERT, to some of the more recent models, Falcons. And the presentation is designed to just as perhaps a busy man's or a busy person's overview on these specific themes, that is pre-training data sets that enable this technology of large language models. So let's get started. And if you're curious a little bit about myself, I'm Jennifer. I work as a postdoctoral researcher and lead NLP services development for the Open Research Knowledge Graph project. I have given a shorter version of this talk at the KGSWC, or Knowledge Graph and Semantic Web Conference Winter School, on November 7, 2023, post which I decided to extend the talk a little bit with some missing parts and release it on my YouTube channel. So let's get started. I guess we can get started by establishing some common ground in terms of just clarifying the large language models and a description of it. So an LLM is a type of a machine learning model that is trained on massive amounts of text data to generate natural language text. So they're essentially neural network models that use deep learning techniques, which enable them to learn statistical patterns in language data, based on which they can generate text that is grammatically correct and semantically meaningful. What's interesting is, as they are scaled, they unlock new capabilities, such as translating foreign languages, writing code, and more. These LLMs, of course, as the name suggests, can be quite large, with billions of parameters, and they require significant compute power and data to train effectively. Two most notable LLMs, or LLM families, we could say, is one of the earliest released in this line of work. So that was Google's BERT model, and of course, the more groundbreaking work from OpenAI in terms of their GPT models. So these models have essentially achieved impressive results in various NLP tasks, including language translation, question answering, and text generation. So this table basically offers a timeline overview of some of the earliest large language models that were released between the years 2018 to 2021. So we see one of the first models was LLaMA, released by the Allen AI Institute, and then OpenAI stepped in with its GPT series. Google as an organization has also contributed very early in the field, as has Facebook, which is now known as Meta AI. And these organizations, of course, amongst others, such as NVIDIA or Microsoft, have also contributed to early research around LLMs. So basically, we could take away a few insights from these early LLMs released in terms of certain characteristics. So first of all, increase in size. First of all, what do we mean by large, in other words? With the advances in hardware, the size of neural language models began to skyrocket. Especially hardware in terms of GPUs. So the examples we saw showed that model sizes early on increased by over 5,000 times in just 4 years. Second characteristic can be seen as emergence. So what difference does scale make? This was basically seen as a surprising thing, basically that just by scaling up these models, new emergent behavior began to be observed. So basically capabilities that the model was not known to have been explicitly trained on. So these LLMs were showing to demonstrate such behavior, for example, behaving like a Linux kernel or so on. And in this regard, I'd like to point us to this initiative called the Beyond the Imitation Game project by Google, led mostly by Google and also hosted on GitHub, where they're collecting emergent tasks that various people from the community might have observed. So now we look at some of the LLMs that are released more recently, so between 2022 and 23. So there was this seminal work from DeepMind called the Chinchilla paper, where they offer certain suggestions or strategies to produce compute optimal large language models. Of course, Google released large-scale, much larger scale models with its PaLM work at 540 billion. So Meta AI also continued to produce large language models, and LLaMA is one of its most notable works more recently as well. And then there was models, multilingual large language models as well. OpenAI continued to improve and release high-performant variants of its GPT model series. Stanford produced some research showing how to obtain small-scale language models that are suitable in academic research scenarios or academic compute facilities. And of course, there is also the organization TII, so Technology Innovation Institute at Abu Dhabi, that also created a large language model. So as you can see, demographically and also organization-wise, various organizations have contributed to this field of LLMs, and of course continue to do so. So now we come to the main central theme of this talk, that's datasets used for pre-training these LLMs. So let's start by clarifying what we mean by pre-training. So pre-training essentially is the process where models are trained on huge quantities of data, which helps them comprehend a broad range of language patterns and constructs. Now, pre-training datasets themselves are foundational to creating optimal LLMs for a variety of reasons, and some of which could be they facilitate broad language understanding. A large enough pre-training dataset could also act as a shared knowledge base. If it models different genres, it can facilitate efficient transfer learning for the LLM. Again, they can be sources of context and world knowledge, and they also facilitate generalization and scalability. So if it's large enough, there are patterns recurring in the data, so this enables the LLMs to generalize over such patterns. Okay, so the plan for the talk is then to visit of course, not all LLMs, but a certain set of LLMs, particularly with respect to their pre-training datasets. So LLMs whose pre-training datasets have actually contributed to moving or pushing the frontiers of state-of-the-art research in producing downstream effective LLMs. So certain strategies that were used to creating these pre-training datasets. In this context, the models we will visit will be categorized by their pre-training architectures based on the essential piece of transformer technology. And in this regard, let's take a quick overview of these different pre-training architectures in terms of their descriptions. So, okay, so there is the encoder-only variant of the transformer architecture. So this variant basically captures bidirectional context, so context from the left and the right of the tokens. So that's what this architecture enables. And thus it's very good for natural language understanding tasks. Models that use this architecture are very good at natural language understanding tasks generally. Some examples would be BERT, Roberta, Albert, and so on. Then there is the decoder-only architecture variant of the transformer. So unlike the encoder, the decoder-only architecture models unidirectional context. So that's context either, so access to either the left or the right context. So these models are great at natural language generation tasks. So the model needs to predict the next token given a sequence of preceding tokens. So examples, of course, is the notable GPT series, Falcon, LLaMA, and so on. And then there is the encoder-decoder architecture, which combines both models. Basically, the encoder creates a semantic representation of the input text, which is then fed to the decoder that then operates in an autoregressive manner, given the input text and predicting the next token and feeding that back into the input. So encoder-decoder architectures, as one might see, are good at sequence-to-sequence tasks or translation or summarization tasks. So sequence-to-sequence tasks such as translation, summarization, and so on. And here some notable examples are BART, Pegasus, mbart, etc. So back to the main plan for the talk, now that we've just briefly visited what each of these pre-training architectures reflect. Let's start with the models and specifically the pre-training datasets powering these models for a model in the Encoder-Decoder family. So a prominent model here is T5, which was released in the paper Exploring the Limits of Transfer Learning with the Unified Text-to-Text Transformer. So the key idea of this work was to model every NLP problem as a text-to-text task or a sequence-to-sequence generation task. And here's what a conceptual model of it looked like. So each of these boxes corresponds to a unique task. So here is translation, here is computing the linguistic acceptability of a sentence, here is computing how similar two sentences are, here is a summarization task. So essentially the model works, so this is fed into the model and it knows which task to perform and produces the output itself as a text. This is regardless if the output is expected as a number or is expected as a class. So that's the novelty of the T5 model. So coming to the pre-training data that powers T5, let's start with the data source. So Common Crawl was the data source used to produce the pre-training data set for T5. So the Common Crawl initiative is a nonprofit organization that conducts large-scale web crawling to create and maintain an openly accessible archive of web content for research and public use. So it basically takes a snapshot of the entire World Wide Web and makes that freely available for public use. And a typical dump of Common Crawl looks as shown in the figure below. So there is your typical Wikipedia page. There might be some product pages. And of course, there are noisy sites with some gibberish text. So this reflects the state of the web essentially. It's noisy and it includes a lot of stuff that is in natural language text, including code. So the authors of T5 hypothesized that one could obtain a more effective pre-trained model if the web could be cleaned in some way. So essentially, they came up with a set of lightweight heuristics that actually pruned out undesirable text from web pages, which resultingly created a text or selected text as shown in the red boxes. So they used a heuristic-based approach, and some of their heuristics looked as follows. First of all, they removed all lines that didn't end with a punctuation. So these got rid of a lot of the menu items. Then surprisingly, they noticed a lot of web pages have this text, please activate JavaScript on your browser or so on. And so they simply eliminated sentences that had the word JavaScript. They also removed all text that had curly braces. So they didn't want to include code, just natural language text. And they also did deduplications using the method of sliding window. And finally, they used the LangDetect library to select sentences only in English. So this filtered version of Common Crawl, as they said, then comprised 700 gigabytes of English text from terabytes of original data. The resulting pre-trained dataset from Common Crawl, after applying their filtering heuristics, they called as the Colossal Cleaned Crawled Corpus, or C4 in short. And this dataset was publicly released on the TensorFlow library. And I thought it presents a great academic exercise to recreate a clean version of the web. So first of all, the Common Crawl corpus is publicly, the Common Crawl dataset itself is publicly available, and their filtering heuristics, the code of their filtering heuristics is also publicly released. So anybody can apply it and recreate the C4 corpus. Right, so in terms of language modeling itself, right? So now we have this C4 corpus. So how was the language modeling task done for T5? It was done in terms of the span corruption objective. So certain spans of text were corrupted in the pre-training corpus, and the model had to learn to predict these spans of text. So that was how it was trained to be a language model. And of course, in the first, one of the earlier slides presenting T5, we saw that it could handle various tasks in a text-to-text generation manner. And this was done as a separate fine-tuning step after pre-training, where each task data set was modeled in the following way. So there was a code, and that code represented the instruction that the model should recognize when the input comes in. And of course, then the input text, and then the model learns to produce the output as desired. Okay, so this was T5, and we saw that T5 made use of the C4 pre-training data set, so a large-scale web data set. And of course, C4 was then a cleaned version of the Common Crawl, or a snapshot of the web. So now let's take a look at a model with respect to its pre-training data set in the encoder model family. So with this, we take actually a few steps back, starting at the very early stages of research on this topic of LLMs, or at least models that were released that facilitated LLMs. So BERT. BERT was work that was described in the paper Pre-training of Bidirectional Transformers for Language Understanding. And indeed, as the name suggests, it leveraged the encoder architecture variant of transformers in the context of pre-training a bidirectional model. And here's what the training essentially looked like. So the first stage was pre-training BERT on a large corpus. And the second step was given a downstream task data set to make some modifications to neural architecture, neural deep learning architecture, and sort of fine-tune the pre-trained model on an architectural variant on a specially adapted architecture that's suited to the downstream task. So let's say it was NER, so they fitted a CRF layer on top of the BERT architecture. Okay, so in terms of pre-training data sets, there were two main data sets used in the case of pre-training BERT. One was the BooksCorpus. So here we are seeing the genre of prose. So this was a corpus of fiction books from various genres comprising 800 million words. And then we see encyclopedia text as well. So basically they use the English Wikipedia. So they extracted only the text passages from Wikipedia and ignored lists, tables, headers, and so on, resulting in 2,500 million words. So what's interesting about BERT is that it began to use document level context, so longer context in training or pre-training the language model. So up until the time of this work, the most common corpus that folks used to train large language model was the 1 billion word corpus. And as you can see, it just had on average 27 words. So this didn't allow the language model to indeed model long range dependencies. And of course, BERT, by using the BooksCorpus and Wikipedia, started tapping into the power of language models to model long range dependencies or long range context. Okay, so just quickly evaluations. How successful was BERT? So at the time of its release in 2018, October, Fine-tuned BERT large, so that was at 340 million parameters. It could outperform sorter models that were specifically tailored or engineered for the downstream tasks. So there would be a specifically engineered model for each of these tasks, as well as GPT-1. So the GPT-1 work was released before BERT came out, very close to before BERT came out. So as you can see, the BERT models were the first breakthrough showing the power of the pre-training objective to obtain strong downstream model performances. Okay, so now we will start looking at the decoder-only models. But before we do that, we may have noticed, or you may have noticed, that most of the recent state-of-the-art LLMs mostly use the decoder-only architecture variant. So this architectural variant of transformers has seen much success in its application for recent large language models. So what may have been a factor for this? So we could just quickly take a look. We could say that the reason is, one of the reasons being the autoregressive versus autoencoder architecture. So the architecture itself. So models such as GPT, which are decoder-only models, generate text sequences one token at a time from left to right. So they are basically autoregressive models. And which model a unidirectional context, essentially suited for text generation tasks. So this nature is well suited for a large range of language generation tasks like text completion, generation, and translation. On the other hand, the other competing architectural variant, let's say autoencoders or encoder-only models like BERT, they're designed as autoencoders, so they focus on capturing bidirectional contextual embeddings. While this is beneficial for downstream natural language understanding tasks, it doesn't directly lend itself to text generation tasks like autoregressive models do. So text generation tasks offer more flexibility in modeling different kinds of task objectives. So decoder-only models, because of their text generation objective, can perform with more versatility in the case of downstream tasks compared to encoder-only models. Okay, so now let's take a look at some models in the decoder-only family, and of course, a closer look at their pre-training data sets. So the most popular model in this would be the GPT series, and the slide basically shows you a timeline of when the GPT series models were released. And in this presentation, I will go over 3 of the models which had accompanying research papers. So there was enough insights into, at least enough insights into the portion of the pre-training data set that went into producing these models. So let's start with GPT-1, the first model that was released in the GPT series. This model was discussed in the paper, Language Models Are Few Short Learners. And of course, this was the first model to be released in the series. So the key idea here was indeed the application of the decoder strategy or the generative pre-training strategy to produce a general and, in a sense, task agnostic model. So the generative pre-training of a language model was carried out on a diverse corpora of unlabeled text together with discriminative fine-tuning on each specific task. And another contribution or a key idea was the choice of the pre-training corpus that also allowed modeling long-range dependencies. So note, I mentioned this in the context of the BERT work, and GPT-1 and BERT were released roughly around the same time. In terms of its pre-training data sources, GPT-1 also relied on the BooksCorpus dataset. So this was, here we are going towards modeling long-range dependencies as well as coherent storytelling patterns using a corpus of fiction books. And of course, to highlight that up until that time, where GPT-1 and BERT were produced roughly around the same time, the longest context model was like just 27 words, whereas The BooksCorpus has 20K words on average, so that's significantly larger than much of the corpora that we used to produce language models at the time. And thus the LLM was able to practice long-range dependency modeling. So this is one of the first contributions from the earlier works, which subsequent works just took on. Okay, so in terms of producing the language model itself, given a pre-training corpus, the researchers for GPT-1 addressed generative pre-training and discriminative fine-tuning in one pass. And how did they do it? Okay, so basically this desk of sorts has all the math that goes into the training objective. Training and tuning objectives. So here, basically, in red, you see the pre-training objectives. So the language model predicts the next token given a sequence of tokens and some parameters. And here you basically see the classification objective or the discriminative fine-tuning objective. So the language model predicts a class given some input token. And these models were, these objectives were then combined into one formula that were trained simultaneously. And that's how it combined generative pre-training and discriminative fine-tuning together. So a training question would be, okay, we have these objectives, but how about the input data? So in the input data, doesn't the classification task need to be represented different than the pre-training task? So this was also a specific contribution of the paper, and interestingly, they used the text as it is. However, they relied on special structural symbols, which they introduced into the text, wherein those structural symbols learned the parameters necessary for a classification task, and otherwise the text was treated simply in a generative objective. So here you basically see input text representations for different kinds of classes. And as you can see, this is like a generative objective. So it's basically a sequence of contiguous tokens, but for a task, they use certain structural tokens like dollars or delimiters as indicators of the classification task. So this was a key idea in the GPT-1 work. So there we see the contribution in terms of the pre-training data set was kind of similar to BERT. So you're basically modeling long-range dependencies, and different from BERT, it didn't train separate models for each downstream task, but modeled the fine-tuning objective with the help of special structural symbols inserted into the input data. So now we come to GPT-2. This is the second in the model series, in the GPT model series. And this model was discussed in the paper, Language Models Are Unsupervised Multitask Learners. So let's take a look at the key ideas of this work. So here we begin to see the first traces of the bigger is better paradigm, right? So this was one of the seminal works that demonstrated that language models begin to learn tasks like question answering, machine translation, summarization, without needing any explicit supervision. So note the title is Language Models Are Unsupervised Multitask Learners. And they can do this when they are trained on a very large scale, in the order of millions, generic data set of web pages. So quite an interesting contribution or observation here from this work. So pre-training data sources. So up until this point, most prior work trained large language models on single domain of text. So this would be news articles, Wikipedia, or fiction books. So GPT-2 is one of the seminal works to explore a large-scale data set of a generic nature as web pages. So this basically set the precedent for almost all following works on large language models that have relied on web pages in a greater capacity. So now when we talk about web pages as a data set, and we've already briefly seen this in the T5 work, we need to say, okay, what do we need from these web pages? So one observes that there is a lot of messy data on the web. So essentially, how to retrieve web links that point to legitimate web pages. So they wanted to create a web scrape that emphasized web page or document quality. So they wanted to create this based on web links that were curated by humans. Of course, to do this task manually is absolutely forbidding. Instead, they used this clever strategy where they went on Reddit and they selected all the Reddit posts that were upvoted at least 3 times, and specifically the posts that released web links. And so they scraped the text from the web links of these upvoted Reddit posts. So this was an indirect method of using the human curation strategy for high quality web pages, for selecting high quality web pages. So the subsequent corpora that they created from this method was called WebText. And this corpus contained over 8 million documents for a total of 40 gigabytes of text. Of course, we saw so how is the language model produced then? So we saw in the GPT-1 work that the generative pre-training and discriminative fine-tuning strategies were applied together at one time to produce the downstream model. In the case of GPT-2, notably, only the generative pre-training strategy was applied, so no classification. So here we basically contrast the GPT-1 work with the GPT-2 work. As you can see, in terms of size, GPT-2 is significantly larger than GPT-1. It had 10 times more parameters than GPT-1. And there was no fine-tuning applied to GPT-2, while GPT-1 was actually fine-tuned for each specific downstream task. So thus GPT-2 can be seen as a pure language model. But of course, we have the trailing question, then how can it perform different tasks? Right, so essentially, how does GPT-2 work on multiple tasks without fine-tuning? So let's compare their language modeling objectives. GPT-1 predicted the output given the input tokens, while GPT-2 predicted the output given the input and some task tokens. So that's interesting. But now we might think, okay, so did they have to create, task-specific data sets for each task they wanted to model? And the answer to this is no. Here you can see an expected input representation to the model. So the model sees a sequence of tokens and it says, okay, I need to predict the next token. That's what I understand from here. In another case, the model sees a sequence of tokens and it sees an instruction and then it understands, okay, I need to translate these sequence of tokens. And curiously, unlike GPT-1, there was no task-specific data set used to train GPT-2. So it was entirely unsupervised. So how did they do it? Well, instead, they relied on leveraging a large-scale data set, and within the data set, they relied on instructions that naturally occurred in the sequence of text. So when the model sees sufficient amount of data with these naturally occurring instructions, it then learns to generalize a certain task in itself. And in this case, multiple tasks, since the language model was, since the pre-training data set was quite diverse. So this screen basically highlights examples of the machine translation task encoded in the running text obtained from the web. So encoded in a sense, not artificially, but naturally occurring. So for example, we take a look at the first sentence. I'm not the cleverest man in the world, but like they say in French, and then the translation. So like they say in French, this was seen to be the task instruction, and such kinds of sequences of text were the researchers then hoped that the model would be able to generalize and learn a task based on these sequences. It might be interesting to see how successful the model was in terms of the zero-shot task performance test. So this model now, the GPT models released in various parameter sizes, was the only model up until that point that was not exclusively trained on specific tasks. And it was interesting to see that this so-called task agnostic model trained with this pre-training data strategy on a very large-scale data set outperformed the state-of-the-art models that were trained specifically for the downstream tasks. So thus they arrived at their conclusion that large language models or language models trained on large-scale pre-training corpora are indeed unsupervised multitask learners. Okay, so that was GPT-2. Now we go on to the GPT-3 work. And this work was discussed in the paper, Language Models Are Few Shot Learners. So the key idea in this paper, so as we've seen before, so it basically built on the preceding research, right? So scaling up language models greatly improves task-agnostic performance, greatly improves performance in a task-agnostic way, or it can learn downstream tasks agnostically. But can the model performances be further increased, or can the model be better aligned to the human output if it's shown a few examples of the task in the context, successful completion? So that's few-shot performance. So this was one of the first papers to formally introduce the in-context learning strategy via few-shot demonstrations. The pre-training model architecture was quite similar to GPT-2, except now this training data set size is significantly further increased, and also multiple data genres were introduced. So here we are seeing web pages. So this work came after the T5 work, and so they were able to leverage the C4 data set. However, they don't just rely on web pages or the Common Crawl dataset. They also add other diverse sources. So they added an expanded version of the WebText dataset that was used in the GPT-2 paper. They added some large-scale BooksCorpus fiction books. They also added the encyclopedia of Wikipedia. So here you basically see a list of the data sets that were pre-training data sets, at least the open source pre-trained data sets. So they did use some proprietary data of which we know nothing about. And yes, so here you see basically the distribution of the raw data in terms of the number of tokens and the sample size. So how much proportion of this raw data was used in training GPT-3, which then resulted in a corpus that was 300 billion tokens in size. So now we revisit the central thesis of the work. So is this significantly larger model able to perform a task better, not only when it sees naturally occurring task-specific tokens, not only learned in this unsupervised way, but also successful task examples? So this is the seminal work to introduce the concept of in-context learning, as we've mentioned before. So let's take a look at the evaluation settings, which was introduced here. So there was the zero-shot evaluation setting where the model is just given the task instruction and expected to perform the task. There is the one-shot setting, which is new here. So the model is actually given an example, a successful example of the desired task, and then is given a task instruction for a new data instance. And finally, the few-shot setting, where the model is not just shown one successful example of the task, but several successful examples, and then given an instruction to perform the task on a new data instance. So what this setting obviates is producing an efficiently performing downstream model without the need to harness additional compute to fine-tune the model. Okay, so GPT-3 was released in various sizes, so at least 8 different models and different parameter sizes with different layers. So this is where we are talking about deep learning models. And note that 175 billion GPT-3 was 100 times larger than the 1.5 billion GPT-2 model that went before it. So it really pushed the frontiers of having large models. And indeed, the bigger is better paradigm. So their larger models were indeed more effective at different tasks. So now we test their hypothesis. Are large language models indeed few-shot learners? So here they test the different evaluation settings for finding out the central thesis of the work. So the x-axis corresponds to the model sizes and the y-axis corresponds to aggregated accuracy over 42 accuracy denominated benchmarks. So these are aggregated scores. So as we see, while the zero-shot performance improves steadily with model size, the few-shot performance increases more rapidly, demonstrating that larger models are indeed more proficient at in-context learning. So some takeaways from the GPT series is its research trajectory, of course, that bigger seems to be better. And their underlying hypothesis. Larger language models encode more parameters that can be interpreted as actual and diverse representations of human language. Okay, so that basically sums up the OpenAI's GPT models. So now we come to open source research, specifically the GPT-J model, which was a 6 billion parameter autoregressive model. So this wasn't released by OpenAI, but by researchers at another company or another organization called EleuthorAI. And their aim was to release just as effective a variant of the GPT models, but which was completely open source and which was also available at a reasonable amount of compute available to the general population. So 6 billion as opposed to, a scary 175 billion. Okay, so a gist of the key idea was that was as follows. Given a set compute budget where one cannot obtain 100 billion parameter model, say, can effective LLMs still be produced? And their idea was to claim yes, if the underlying pre-training data set can be diverse enough. So that was their central idea that they were trying to explore. And of course, the contribution was the pre-training data set itself. And this is known as the pile corpus in the community. That was indeed a corpus of open source data that modeled diverse text genres, which was a unique and open accessible resource at the time. And that corpus was first created, of course, and this model was trained on this corpus and tried to show if it was effective indeed. So the subsequent, in this talk, subsequently, I will be focusing only on the pile corpus and describing its details. So GPT-J then trained on the pile, gained popularity as an accessible alternative for researchers and developers who want to experiment with LLMs without the high computational costs typically associated with them. All right, so now we come to the pile corpus. So this corpus itself was released in a paper called The Pile, an 800 gigabyte data set of diverse text for language modeling. So essentially the title says it all about its objectives. So the key idea was increased training dataset diversity would improve general cross-domain knowledge and downstream generalization capability of LLMs. So the corpus itself is 825 gigabytes, English text corpus, and it's constructed from 22 diverse high-quality subsets, both existing as well as newly constructed as part of this work. So what are some of its data sources? It has PubMed, Archive, GitHub, free law projects, Stack Exchange, US Patent and Trademark Office data, PubMed data, Ubuntu data, Hacker News, YouTube captions, philosophy papers, and so on. Additionally, it also created new variants of the books, fiction books corpus. Okay, so on this slide, you basically see a composition of the pile by category. So blue, academic, green, internet, orange, prose, yellow, dialogue data, and miscellaneous. So as you can see so far, this is the most diverse corpus that existed up until that time. So let's visit each category quickly. So starting with the internet data set, PileCC was nothing but a process version of Common Crawl using another tool called JustText. WebText is similar to the WebText corpus used to train GPT-2, except it used a more recent version of Reddit. So it updated the data set basically with more recent upvoted Reddit posts that shared web links from which the web content was scraped. And of course, Stack Exchange, which is the largest community QA platform, whose data set is also publicly available, covering subjects from programming to gardening to Buddhism and so on. And of course, the encyclopedia Wikipedia. Then there was the academic data set, PubMed Central. PubMed Central is a subset of PubMed, which is run by the US National Center for Biotechnology Information, NCBI. So PubMed Central provides open full-text access to nearly 5 million biomedical publications. So they also use Archive, which is a source of high-quality math, computer science, physics papers. Free Law, which has multiple data sources, one of which that was included in this data provided bulk downloads for millions of legal opinions from federal and state courts. Then USPTO, which was the US Patents and Trades Office corpus that provided the background sections of patents granted by the US Patents Office. And the background sections are often written in less strict academic writing so that they are accessible to the general audience. There was a corpus of philosophy papers, and the remaining two are also biomedical data sources. Then there was the prose dataset, starting with Bibliothèque or Books 3 corpus. This consists of a mixture of fiction and nonfiction books. And of course, as we saw from the seminal BERT work and GPT-1, books are invaluable sources for long-range context modeling as well as coherent storytelling. Then there was the PG-19 corpus, which was the Project Gutenberg dataset of classic Western literature from before 1919. So this represents a distinct style of literature than the more modern Books 3 corpus. Then there was the BC2 corpus, which was books written by as of yet unpublished authors. So these two corpora were written by published actually. And then we come to the dialogues data set. So this was subtitles, so obtained from YouTube, a parallel corpus of the closed captions. And of course, they cover a rich set of sources, so educational content, popular culture, natural dialogue. There was the Ubuntu IRC corpus, which had all the chat logs of Ubuntu-related channels. And it's unique since it features a level of spontaneity with respect to real-time human interactions that are not typically found in other models of social media. Then there is, of course, the Europarl corpus, which is a parallel corpus of the proceedings of the European Parliament in 21 different European languages. The Hacker News corpus, which was commentaries of user-submitted stories on topics from CS to entrepreneurship. And this might be a typo, but this was the Enron emails corpus, which is a valuable corpus commonly used for research about usage patterns of email. And of course, there were the miscellaneous data sets, so GitHub for code and mathematics data. So this table just shows you an overview of the data set, the sampling proportions, the number of times the corpus was repeated, and of course the effective size that was then used. And so the link to the entire data set is available online. So returning back to the GPT-J model, right? So the pile corpus was then used to pre-train GPT-J, an open source model, and revisiting the key idea. They wanted to examine, given a set compute budget that cannot be as large as 100 billion, that cannot support such a model, can effective LLMs still be produced? So, so their claim was, yes, if the underlying pre-training data set is diverse enough. So we could only see how effective this was in terms of the results. So briefly to discuss the results, this model, since it's an open source variant or posed as an open source competitor to the OpenAI's GPT models, was then compared to indeed the GPT-3 models itself. So when neither of the models is fine-tuned, that's the GPT from OpenAI as well as GPT-J, GPT-J 6 billion was seen to perform as well as the 6.7 billion parameter GPT-3 Curie model on a variety of tasks. Furthermore, it outperformed the 175 billion parameter GPT-3 Da Vinci model on code generation tasks. And with fine-tuning, GPT-J outperformed an untuned GPT-3 175 billion Da Vinci model on a number of tasks. So you could see that indeed their claim was proven true. All right, so that's the pile pre-training corpus, a diverse, large-scale corpus to produce optimal downstream LLMs, competitive with some of the closed source models that rely on a larger proprietary data. Okay, so now we come to another line of work, and this was by researchers at Meta AI. So this is the first model in the series. This model was released in the paper LLaMA, Open and Efficient Foundation Language Models. Okay, so the key idea. Now, the key idea in this paper can be contextualized given existing lines of thought. So on the one hand, folks at OpenAI were exploring bigger is better. And on the other hand, folks were exploring having optimal models for a given compute budget, right? Basically, we saw that GPT-J tested a diverse enough large-scale data set. So LLaMA somehow follows along this line of thought. So it says, for any given inference budget, so it just doesn't restrict itself to a small scale. So it says 7 billion, 13 billion, 33 billion, 65 billion. How does one obtain the most optimal model? So that's the question that was explored. And indeed, their method or their proposal was, for the given inference budget, train on more tokens than typically used. So in other words, the hypothesis tests if a model for a given inference budget, but trained on much more tokens, can outperform a larger model. So, and they found that LLaMA 13 billion indeed outperformed a 10 times larger GPT-3 on most benchmarks. And the larger model, LLaMA 65 billion, was competitive with the best models at the time. So Chinchilla 70 billion and Palm 540 billion. So, specifically, they surpassed all preceding models because LLaMA was trained on many more tokens than were the preceding models. So LLaMA was trained on 1.4 trillions of tokens, so exceeding the billions that before models used. So it showed that it was possible to train state-of-the-art models using publicly available datasets exclusively without resorting to proprietary and inaccessible data. So, of course, all the best models at the time, that is GPT-3, Chinchilla, Palm, were trained on proprietary datasets. So in terms of pre-training data sources, it did rely on web pages, so specifically the English Common Crawl. In terms of novelty, the English Common Crawl was processed by the CCNet pipeline. So let's take a look at the CCNet pipeline. So this pipeline for processing the Common Crawl distinguishes itself from the pipeline that was used in the T5 work, okay? And it was described in the paper, CCNet extracting high-quality monolingual datasets from web crawl data. So it used a new set of steps to process the Common Crawl. And let's see what they were. First of all, it carried out deduplication, so it did normalization of the text in terms of lowercasing the characters, replacing numbers by placeholders, and so on. And it also did, it used an algorithmic way by leveraging the SHA-1 hashing method for deduplication, and also optimally deduplicating it. So this was very effective in getting rid of a lot of boilerplates, such as navigation menus, cookie warnings, and contact information. And it also removed a significant amount of English content from non-English web pages. As a second step, what it did was language identification. So it split the data per language using the language classifier from FastText. So it didn't just want to produce English language data set, but it wanted to produce different data sets for respective languages. And thirdly, it used an n-gram language model to detect high-quality content in the web page as opposed to low-quality content. And this was measured in terms of perplexity score compared with a model trained on Wikipedia. So Wikipedia was seen as a high-quality data source. And so if the language model performed poorly on Wikipedia or had a high perplexity on Wikipedia, then it was low-quality content as opposed to another model that had a low perplexity on Wikipedia. So when CCNet, so CCNet was put to the test initially, separately from the LLaMA work, of course. LLaMA leveraged CCNet in its work, but in the CCNet work itself, it was applied on the February 2019 snapshot of Common Crawl, and it produced 3.2 terabytes of compressed documents in 174 languages. So in terms of tokens, the most prominent were English, Russian, Chinese. In terms of documents, the most prominent were English, Russian, German. As a side note, one might also consider Common Crawl as a good source for low resource languages. So there is the Afrikaans language, there's Gujarati, there's Khmer and Burmese and so on. Okay, so now back to the LLaMA work. So they processed Common Crawl from 2017 to 2020, processed by the CCNet pipeline indeed. Additionally, web pages, as a further measure of quality, web pages that were not used as references in Wikipedia were filtered out, so they did not scrape content from those web pages. Additionally, they used the C4 dataset containing nearly 1 trillion words. Now, a distinction between the CCNet processing pipeline and the C4 processing pipeline was C4 was entirely heuristic-based, while CCNet pipeline was algorithmic. So that was a bit of a distinction there, and hence they could obtain diverse data from the application of those distinct processing pipelines. In addition, they included other diverse sources. So now we are seeing people going towards capturing diversity in data sets. So they included code, encyclopedia, Wikipedia, BooksCorpus, scholarly articles, and question answering from Stack Exchange. So here you basically see the sampling proportions of each corpus included. So the entire training data set roughly consisted of 1 trillion tokens after tokenization using the byte-pair encoding algorithm. So for most of the training data, each token was seen only once, except for Wikipedia and the BooksCorpus. Okay, so now to test their hypothesis, right, given this pre-training scenario. So has training, where they have trillions of tokens, right, much significantly larger than what went before. So has training on more tokens helped? Furthermore, is it possible to obtain high-performing models on only open source data sets? So this table basically shows a comparison of LLaMA models in various sizes against the state-of-the-art models which were trained on both open source as well as proprietary data sets. So basically, LLaMA 13 billion outperformed GPT 3.5 on most of the data sets, and note GPT-3 was 175 billion parameters, so significantly larger than 13 billion. And of course, the largest model is better than Chinchilla and Palm 540 billion on most data sets. So that was basically the LLaMA work and a little bit of a perspective on its pre-training data set in terms of the fact that it really moved the needle on the leaderboards of large language model. Which brings us to Falcon. Falcon is a more recent work that was performed at research at an institution in Abu Dhabi by a group of researchers there, and also producing the state-of-the-art model. It was released in a blog post that said Falcon, an open large language model with state-of-the-art performance. Complementary to the preceding work, the Falcon LLM placed further emphasis on the pre-training dataset quality. So this one took it another notch higher to obtain high-quality dataset and to implement a methodology that could actually produce a high-quality dataset. Also, Falcon, like LLaMA, is trained on trillions of tokens of text, but GPT-3 was trained only on billions, and it's using that as a competitor. Of course, as I speak and record this presentation, GPT-4 has already competed on the size of the training dataset. Nevertheless, the largest Falcon model was a more compact, trained on trillions of tokens, but a more compact model in terms of parameters, while GPT-4 is rumored to have trillions of parameters. And also importantly, and of interest to the research community, is that the Falcon models cleanly support democratized access to LLMs. So they are available under the Apache 2.0 license, while the GPT-2 models are all closed source. So variants of Falcon models, there are variants of the models released as well. So Falcon Instructor, Falcon Chat. And at the time of its release, that is May 2023, the fine-tuned Falcon model beat all other models, such as LLaMA 1 or GPT-3. And it was the state-of-the-art on the Hugging Face leaderboard. Okay, so a key ingredient, and very curiously so, for the high quality of the Falcon models was their training data, which was predominantly open source, and which they called as the RefinedWeb corpus. So the RefinedWeb corpus was the novel massive web dataset based on Common Crawl. So what is this RefinedWeb corpus? Let's take a closer look next. So LLMs, of course, until that point were trained on a mixture of filtered web data and curated high-quality corpora, right? So this table basically shows you an overview of the data sets that were used to train a large language model. So GPT-3, of course, there's no name for this data set, so that's just represented by the name of the model. And what you can see here in this column is that these models that were highly successful with large number of parameters relied only on a portion of the web, while the rest of the data was closed source proprietary data, right? So on the other hand, the RefinedWeb corpus that was used to train Falcon was 100% from the web. Okay, and of course, the closest dataset to the RefinedWeb was the C4 dataset, introduced in the context of the T5 model. But note that RefinedWeb was significantly larger than C4. Okay, so in terms of processing, RefinedWeb, like C4, also relied on the Common Crawl, but they implemented new processing methods like URL block list and so on. Furthermore, RefinedWeb, when compared to C4, also implemented more sophisticated web page deduplication strategy. So they used an algorithmic method. Okay, so the central idea for the Falcon team of researchers to create RefinedWeb was the following. So can properly filtered and deduplicated web data alone lead to powerful models? So RefinedWeb comprises 5 trillion tokens from Common Crawl, and they release a portion of this data set publicly, so 600 billion tokens. So let's take a look at this scalable data processing pipeline that resulted in the RefinedWeb. So this is what it looks like. Essentially, there are 3 main parts to the data text processing pipeline. So the first one is document preparation, the second one is filtering, and the third one is deduplication. So let's focus on the first part, that's document preparation. It comprised 3 different steps. URL filtering. So here basically they had a block list of URLs to remove, scored higher URLs. Furthermore, they blocked high quality sources, specifically sources like Wikipedia and so on, because their central thesis of the work is that it's possible to obtain a high quality data set using this processing pipeline from noisy web text data to train an effective downstream model. And they didn't want existing high quality sources like Wikipedia and so on to affect this measure. And hence they excluded this data and said that their pipeline could indeed produce a high quality text at the end. Okay, so another step here was text extraction. So they used some libraries to extract text, and then language identification, for which they used fast text to select English data and so on. Of course, in the second stage, they did filtering. So this was document-wise filtering and line-wise filtering. So this is basically computing maybe symbols to a token ratio. So if there are more symbols on a page, it's maybe noise and it can be eliminated. So that would be the filtering method that was applied at the document level and line-wise level. And finally, deduplication using some sophisticated hashing algorithms. So deduplication at the document level as well as at the URL level. So here is basically an overview of arriving at the final RefinedWeb dataset when different stages of their pipeline were applied. So in the first stage, they got rid of a minimal amount of data, and the language identification really eliminated half of the web. Then the next stage was the filtering stage, which also caused them to have a 23% downstream corpus. And finally, the deduplication stage. So they were sampling only 11% of the original common crawl to arrive at the final high-quality data set. So evaluation. So was this strategy effective? So in other words, can an effective LLM be obtained only from a heuristic-based pipeline that's trained only on data from a heuristics-based pipeline to create a high-quality web data set? So here you basically see different data sets that are standard in the community for benchmarking the performance of LLMs on different tasks. So yeah, it was applied on all of these tasks. And what you see here is a plot of the average evaluation scores versus the compute budget. So what was observed in the case of Falcon, trained only on the RefinedWeb corpus, is for a given similar compute budget, RefinedWeb surpasses models that were like GPT-3, which was trained on both web and closed source proprietary data. So note the pink dots corresponded to models trained only on web data. So thus their research question was ascertained. Of course, given the work that went before, for example, the C4 work or the PILE work discussed in this presentation, these were alternative models to produce a web data set for training large language models. So what they did as well in this work is applied the RefinedWeb strategy to each of these existing data sets. And they saw that given the RefinedWeb strategy, a significant portion or a sizable portion of existing data sets could still be reduced or filtered for quality. And furthermore, training or retraining the models on these filtered data sets boosted their performance furthermore. Thus, the resulting conclusion could be that the quality of the pre-training dataset is critical to downstream LLM performance. Okay, so in summary of RefinedWeb, stringent filtering and deduplication could result in a 5 trillion tokens web-only dataset suitable to produce models competitive with the state-of-the-art. Right, they publicly released a portion of RefinedWeb, of course. And finally, the Falcon model that was released ultimately was not just trained on RefinedWeb. So it was also trained with a small portion of proprietary data. But we saw the evaluations where it was purely trained on RefinedWeb and still surpassed the performance of GPT-3. So I'm slowly tapering off to the end of my presentation here. So in the realm of works creating pre-training data sets, the RefinedWeb pipeline can be considered the state-of-the-art in terms of producing high-quality downstream web page data. Okay, so on this slide, I basically now show you all of the models that I've talked about, in particular with respect to their training data set. So we can see that the PILE data set is the most diverse. Falcon, more recent data sets are being produced in the trillions of tokens as opposed to billions. And indeed, one could safely say that progress in LLM research is very complementary to the pre-training data sets and the strategies for producing pre-training data sets indeed. So this completes my talk. So some quick takeaways. So as we saw in the GPT-1 work, the choice of the pre-training corpus needed to take into consideration the average context length. So large language models model large contexts, and that's a reason for their success. Secondly, while the GPT series pushed the frontiers of obtaining really large language models, it could be that bigger does not always equal better. So researchers have found that ultimately smaller, more optimal trained models can outshine their behemoth counterparts and require less energy and fewer training sources. So in this case, I would refer the reader to what is called as the Chinchilla paper by Hoffman et al. Okay, then as shown in the RefinedWeb work, the quality of the pre-training data is highly conducive to obtaining effective downstream LLMs. And furthermore, effective downstream LLMs also rely on diverse information representing in the pre-trained dataset. So that's a short summary of my talk. And finally, I will conclude with a cautionary note. So self-supervised or unsupervised training on large corpora of information would mean that it also learns much undesirable behavior that is unfortunately present in human text. So a lot of unsafe content and so on. So this could mean incorrect or misleading medical information or encouraging self-harm and so on. Therefore, it's very important to put in place measures such that the large language models ultimately do not end up offering harmful advice to humans in their applications. With this, I would like to thank you for your attention. Of course, if you're welcome to connect with me on LinkedIn, you can find me at Jennifer-L-D'Souza on LinkedIn. I'm very happy to connect with other researchers on this topic, especially on the topic of large language models. So with this, I end my presentation and see you around.